doesn't matter. That's what's cool, is that, in fact, I will prove it in a second. I mean, we'll see it. It'll pop out of nowhere. I'm going to make an assumption right now that the sum is not 0, because otherwise I couldn't normalize, right? You know, if the sum is non-zero, I can always divide by the sum and make it 1. And then there's a really pretty trick that I'm going to show you. I'll explain what I mean by this in a minute. I'm using this funky notation because things get confusing if I don't. Pi is a row vector, 1's a column vector. I don't need this funky cross in the middle. It's just so you can get lost in the weeds if I don't emphasize I'm making a product. I'm taking a column vector and I'm multiplying it by a row vector. So when I write 1 cross pi, all I'm doing is I'm multiplying a column vector times a row vector. So what that is it's a matrix with all rows the same. You know, that's what happens when you multiply a column vector of all 1s times a row vector. You just repeat that row vector over and over again. Okay? And now what's going to happen is that what happens if I square it? Well, you can see it's really useful that these guys are eigenvectors. Because I'm just going to go and make a big mess of this. I'm going to get a p squared minus 1 cross pi p, this times this, minus p 1 cross pi, and then plus 1 cross pi, 1 cross pi. All right. And remember, I'm just doing the natural thing. This cross is not there, because we're not used to writing products when we multiply matrices together. That is matrix-matrix multiplication, where that's a n by 1 matrix, and that's a 1 by n matrix. It's standard matrix multiplication, and it's associative. I can, instead of first multiplying 1 by pi and then multiplying p, I can take p times 1 and then pi. And what's p times 1? And what's pi of 1? Row vector times 1. It's a dot product. All right? Pi is a row vector. I'm multiplying by 1, which is a column vector. That's what that is. Row vector times column vector. It's a dot product. That's the thing. It's that. All I'm doing is reciting algebra. That's all there is here. It's just the notation scares people, but it's algebra. And so, have you all worked this out? These guys cancel out because I've assumed the sum is 1. So I get the 1 cross pi. That's a p1 1 cross pi. Pi p equals pi. So it's equal to p squared minus 1 cross pi minus 1 cross pi plus 1 cross pi. All right. And so I can do this forever. All right. So basically, this is what I get. So if I do this, so this is a standard trick in linear algebra. What you do is you have a matrix, and you look at its spectrum. The eigenvalues, it's also called the spectrum, and you have an annoying eigenvalue. The annoying eigenvalue here is 1, and you kill it off. And the way you kill it off is what I just did. You take the outer product of the right eigenvector and the left eigenvector from a matrix, And by subtracting it off, you kill off this eigenvalue. So P tilde has the same spectrum, but it loses the eigenvalue at 1. You know? So guess what? P to the tilde n goes to 0. And the reason for that is that, again, the eigenvalues of P tilde and P are identical except for 1. And we could prove that. That I think we'll have to wait for homework or for another time. But it takes a few minutes to prove that. And it all has to do with the orthogonality conditions. It's really trivial to show that these left eigenvectors and right eigenvectors are orthogonal if the lambdas aren't equal. There's a bit of linear algebra to do there. But this fact, so the eigenvalues coincide, the eigenvectors coincide, everything coincides. We're just knocking out one subspace. Right? So we proved the ergodic theorem. You know, I really wanted to prove the ergodic theorem in 30 minutes, and we did it. The ergodic theorem for Markov chains. I made a mistake with language. The unit chain case just means that. Okay, I've made something a little bit stronger. Okay, and that's actually equivalent to what's called aperiodicity. All right, so I made a little boo-boo there. So unit chain is equivalent. When I make the formal definition, the standard definition next week, this means a single eigenvalue at 1. No repeated eigenvalue at 1. Okay, so the ergodic theorem for aperiodic unit chain Markov chains. So we actually get that so, and what do I mean by h, expectation of h of x, expectation of h of x infinity? What the hell is that? Go back and do some pattern recognition. If I hit both sides by h, I get the p to the nh. Well, let's do it. There is no x infinity. This is just notation that's supposed to be suggestive. That's just defined to be equal to the summation of a k of pi of k h of k, right? And that's it. So let's prove it. Proof. It's right there, but let's write it down. Right there. These are matrices. We're not in an abstract operator world. These are matrices. That's an n by n. I shouldn't use n, since n was the size of my state space. But yeah, whatever it is, it's a something by something matrix. That's a matrix. That's a matrix. That's a matrix. It's just the most boring matrix on Earth because all the rows are the same. And H, we're visualizing it now as a column vector, because that's what we're doing. And so that's pi H, it's just a dot product times 1. Cool. That's it. QED. It's just about interpreting this, right? And all right, this is the same thing. All right. It's too easy, that's all. I love this. You all look puzzled. Okay, I mean, I guess the only mystery is I guess maybe it's, there's a little linear algebra there. So there's about 20 minutes of linear algebra to say that all the eigenvectors are the same, all the eigenvalues are the same. So there's some magic there that does take 20 minutes to prove, but that's basic linear algebra. And you probably did see that in a linear algebra course once. I mean, most likely. So what's the rate? So we've got this ergodic theorem. The expectation at time n is a steady state expectation that goes to 0 geometrically fast. What's the rate? If you're a CS person, you would answer instantly. Well, there's no e's. It's all discrete time. Yeah.
It's controlled by that.
So you say yes. So the thing that's typically said is it's the second eigenvalue. So people will say the claim is basically you look at the maximum eigenvalue. Here I made them all the same, it seems like. I should have made one bigger. I don't know. Let's put a couple more over here. No, it's too late. Which one's the biggest? They're all the same. So basically, you take lambda max, and you take its absolute value, and you raise that to the nth power, and that's the rate. That's how quickly it goes to 0. Anybody agree with that? If so, you agree with me that mathematics is overregulated and that Jordan should be put in prison. Does anybody remember Jordan canonical form and what happens? What goes wrong?
The block is Jordan.
Those damn blocks, yeah.
It's hideous.
It's horrible. And that's why he should never have been allowed to have a mathematical license. He was but it turns out that it's just not true. So what happens is you can get a horrible mess, is that you can end up with repeated eigenvalues like that. And if there's k repeated eigenvalues, you're going to get an n to the k minus 1. All right. So the thing is that a lot of models, actually, you can make this claim. We've run out of time, but there's Markov chains that are called reversible, and then the Jordan blocks aren't there, you know. But they never exist in my world. I mean, reversible Markov chains just don't exist. But it's assumed often, just for simplicity, often to get rid of that awful problem, that Jordan block. Yeah. So there's a Jordan canonical form for any matrix, and it corresponds to having this polynomial term as well as a geometric term. And that's why when people actually, there's a big industry of trying to get rates of convergence for Markov chains, because you want to figure out how long do I have to simulate something to get a good estimate of something. And the fact that in big systems like infinite Markov chains, this could be, you know, no longer polynomial. So it's really, it's hard to get some intuition. So when so if you plot this, it could have huge excursions before it settles down. All right, any questions? Yeah.
So the matrix P theta is on the same size as the matrix P, so it must be having a new eigenvalue.
What's that? Well, yeah. So one was an eigenvector for P, a right eigenvector, you know, and then pi was the left eigenvector. It's a row vector, you know. So this is also again, I wish I had used a different letter, but it was n-dimensional vector. I'm using n. I made a big mistake using n for time here, because n was reserved for the size of the state space.
Okay, my question was, if the new eigenvalue that P theta would have besides the n minus 1 that is inherited from P.
Say it again.
Does P theta have a new eigenvalue besides the n minus 1?
No, it's 0. So yeah, p tilde 1 equals 0. So yeah, so it preserves that eigenvector, but it just moves the eigenvalue to 0. And the same with pi. That's what it does. It keeps the eigenvectors unchanged, but it just takes that maximum eigenvalue and maps it to 0. That's all it does. Yeah. So that's a standard algebraic trick you should know. It's really useful. All right. So there's the ergodic theorem for Markov chains. It's proven. And so then the trick then is to kind of map that to something you know. You know, like that diagram I drew before and all of that. How you relate the graph structure to the eigenvector structure. You know, and some of that is like that. You know, and some is not. All right. So that's.
Does this have like the same implications? Like instead of looking at the unit ball, like if it were continuous state space? Like
No, continuous. Wait. This has nothing to do with a finite state space. Nothing at all. So if we were in a general state space, we could do exactly the same thing. Continuous time, you have the right half plane. Absolutely. Left half plane. Yeah, it goes through the continuous time. But of course, you look at the left half plane. Yeah. So it's really, the whole spectral ideas go through in general state spaces.
rather than just
Yeah. Discrete time, continuous time. Yep. All right, we are, I guess, meeting adjourned. And have a good weekend. I promised to send a follow-up about the exam. It's just been busy, but I will. And it's only the P. That's all. I want you to have nightmares about P to the M. That's all I want. All right.